Okay, let's start. So before we start, I have a announcement, one or two announcement. First one, we're gonna have a presentation on Wednesday and Friday. So if you go fast, then we can do more on Wednesday, and Friday presentation will be finished earlier. And when you make a presentation, of course you need to show us your output, but as I said, your output doesn't have to be 100% complete. So even though you have, you know, as long as you have a complete plan, uh, even though you couldn't make it in time, you can still make a presentation and let us know what your future plan or what your goal is, and then we can discuss. And also, I advise you to participate. Every member of your group must participate because I'm going to ask questions for every single member in your group. So it's not for checking whether each member had their work. It's just for having every member equal responsibility of participating the project. Okay, so I don't want one person do all the work because uh, at least this is the project for everyone. I only divide it into groups so that for various reasons, uh, for example, if I let everyone do each project, then it's impossible to uh, do the presentation or make an assessment. Anyway, so don't forget on presentation and also everyone's participation. And the second one, so I get the email about the report often. So report, as I said, can be written individually or in group. Which way is fine. Uh, the report's going to be due after the midterm week. I didn't make an assignment page, but once I make an assignment page, an LMS, I will notice, and then it's probably due by next Wednesday. And if you decided to upload it by yourself, write it by yourself, you can do so. If you are writing one report for group of people, then one person can only submit your work. And as I said, I gave you the template. That template is the template because you're not allowed to use other document or other Word program. So just write the text in that text file, the MD file, markdown file, this one. So I'm not saying that you just copy paste the content in the template. What I'm saying is that you just download the exactly same file ending with the MD, and then edit the content here, and then upload the text file itself. Okay, don't convert it into another thing. Just upload a text file, and if you have an image attached to this text file, I have an instruction how to do it, and also you need to upload it all together. Okay, so that's that. And is there any questions about the presentation or report? Okay, so let's talk about the chain rule. So today we're going to talk about the chain rule. Chain rule. So before I begin the chain rule, I need to emphasize again the meaning of differential. Okay, so differential. I'm going to write a little bit here. I did try talking in the morning class, and I think didn't work well. So I think I'm going to write as I talk. Let's say, okay, what is the differential? So there are many different ways to explain the meaning, but let's restrict our case for the single variable function case first. So in the single variable function case, differential is simply a rate of change. Rate of change of what? What change? So you have a change of input, and because of change of input, you have a change of output. So if I draw the picture here, let's say we have a point x in x-axis, and there is a point y, let's say y0, which gives you the value of function. And if you change the point x0 slightly from left to the left or right, then you change the value of function, right? So delta x is the change of x0, and now delta y is change of y0. You want to measure how much does y change by the change of x. You want to know how you can relate the changes of x and y. That's the rate of change. So the differential is the measurement done by taking the ratio between those changes. So in some sense, it's a number. Usually you recognize this as a number, but you should recognize it as a map. The map that relates the change in the inputs and change in the output. So let me write it this way. So differential is a map that relates the change in the input and the change in the output. So in the single variable function case, how do you relate those changes? If you have change in x, then you get change in y given by just simply multiplying. It's not equal, it's approximately equal, taking this number called differential times delta x. So this is how you relate the changes in x and changes in y. Okay? So now we're going to take that idea, not the same formula, take the idea of a differential and generalize to the second two-variable function case. So in the two-variable function, so what is the differential in this case? Again, without knowing the definition, let's try how we can apply the idea of a differential to the two-variable function case. I want to relate the change in the input to the change of output. So here, let me give an example of two-variable function, z equals to f of x, y. Input is two-dimensional point. Let's say x, y here. And what is the output? Output is just a number. It's a real number. Here I denote it as z. So what do you mean by change of input in this case? So you want to change the point. How do you change the point? So you simply change the point by moving the point. And when you move the point, like in the case of single variable case, you don't want to move long distance. You just want to make a small change. So when you make a small change, the path doesn't matter. Only the direction and speed matters, right? So you only need to know in which direction, in which speed you're going to make a move to that point. So how do you describe this direction and speed? That's the vector. So when you describe a change of point, you're talking about vectors. So you want to relate the change of input, which is a vector, to a change of output, which is now the number because the output is the real number anyway. So change of input is a vector, two-dimensional vector in this case, and change of output is a number or a real number. Now, as I said, differential is the relation that maps changes in input to changes of output. When you are talking about the single variable case, just relate number to number. That was fine. But how do you relate a vector to number? How do you get the formula that connects the vector to number? There you need a matrix. So let's say U is your change vector of point, vector of movement, let's say. I want to make this thing make sense. So movement, what I mean by movement is the change. So this movement is not a long distance movement, it's infinitesimal movement. Infinitesimal movement of the point. Let's say I'm moving in this direction, given by a comma b. Now, how do I know how fast does my value of function change? So how do I know that? So I can take that as a directional derivative, right? So if I move along this direction with this speed, my value of function changes. I want to know how fast that change. So that's the same concept of directional derivative. If I keep moving in this direction, how fast should I move? How fast shall I move? That's the directional derivative. So we have directional derivative of the function at the point is the rate of change of value of function at x0, y0 when the point is moving in the direction and speed of u vector. So let me write vector notation here, right? So then I can know how fast it moves, but now how do I relate this notation, this speed, the speed of change of of the function value with the change of x, change of my input, which is the vector. So then we have to talk about the gradient. We talked about the gradient. So the rate of change is actually given by the inner product between gradient and the vector, the change. Okay. Once you have a change, by taking the inner product with the change, which is the vector, and with the gradient, you get the change of output. You get the speed of change of output, right? So in some sense, you can say this is a differential, which relates the change of input to change of output. So this can be called differential. This has the same role or same functionality as differential. The same role or functionality as the differential because it relates the change of input to change of output. Okay. Now, it doesn't generalize to more general case. If you have more variable as an output and more variable as input, this doesn't generalize. So we have to adopt a notion of matrix. So instead of writing in this way, let me write this way. Since we have the gradient x0, y0 given as the vector whose components are the partial derivative fx and fy. When I take the inner product with another two-dimensional vector, what I really get is just a times f of x plus b times f of y. Here, I'm assuming my u vector is ab here, or just vector ab. I can get the same result by taking multiple of two vectors. Here, first one is f of x, fy, 1 by 2 matrix. And the second one is 2 by 1 matrix, AB. So this is matrix multiplication, a matrix representation of a vector U. And this is what actually we call differential. This is differential as a matrix. Okay. So you have to understand the idea how it flows from the single variable case to the multivariable case. So meaning of the differential generalized to the definition of notation of differential itself. So now let's begin with the slide. We're going to talk about the form of differential here. By the way, this slide is not the same one I put it in the first time. I updated yesterday, so it's gonna be slightly different. So let's talk about differential here. So we are talking about the most general form of multivariable function. It has m number of input, n number of output, and there's still a typo here, but once you get this, then differential at a point A is n by m matrix. Here, this index is typo here, where each entries are given by partial differential of each coordinate function. So on the first row, you take the partial differential of the first coordinate function y1, and the last row, you take the partial differential of the last coordinate function. And each of these entry is not a derivative, it's a differential. It's a number, okay? So you take the partial differential at point A to get actual matrix. So actual matrix, each entries are numbers. So let's think about what that means. So first, let's practice. I mean, I think we practiced before. Maybe I'll do it here without letting you know, letting you do it. So let's try to follow the rule to get the same computation done here. So if I have this function, then what is the differential at 1, 1? Let's just do the same thing. the v is the first coordinate function. It's the formula of in terms of uv. So you should consider this as a two-variable function. Just u is missing by some reason. Maybe the coefficient is 0, whatever. So you can take a partial differential of this coordinate function either in u or v. If you take the coordinate partial differential in u, then it's 0 because v is independent to u. And when you take the partial differential on v, you get 1. So now you get 0 and 1 as the first column entry of your differential. And don't forget, this is constant only because the result doesn't depend on the input, but we need to apply 1, 1 at the end. So about the second coordinate function, it's uv. Now we're going to take the partial differential u and v once, and it's going to be v and u. And when you apply 1, 1, when you plug in 1, 1, then it's simply 0, 1, 1, 1. Okay. Now, I am tempting to say, what does that mean that we have a differential of this function as 2 by 2 matrix of that entry? That means that gives, again, the same meaning of differential that relates the change of input to change of output. Let me show you in this way. So I'm going to write here. So if we have differential at 1, 1 equals to this matrix, then if the point x and y is moving from 1, 1 at the velocity of a, b, then, so here, sorry, not using xy because we used uv case. So let's say my function f is a map that sends a point in uv plane to xy plane. Okay. So I am at the 1, 1 in the uv plane, and I'm assuming my point uv is stationary at 1, 1 at the beginning, but moving in a speed of a, b, and just start to move. And what's going to be my image? When I am at the stationary point 1, 1, it's still in the 1, 1 in xy plane. It just happened to have the same coordinate, but there are different points. 1, 1 in xy is different from 1, 1 in uv. However, when I started to move to the direction of AB, the image point in xy plane will not going to move in the same direction and same speed. We're gonna move in different shape or different direction, and who knows. So let's see. I want to find out if I move just a bit to the direction of AB in my UV plane. I want to know how my point 1, 1 in XY plane moves in which direction and which speed. That's going to be alpha and beta. Then the image 1, 1 in XY plane will start to move in alpha beta velocity. Now, the question is, okay, anyone can say that. What's the relationship between AB and alpha beta? That is given by the matrix multiplication. So if I start to move AB, then the alpha beta that governs the movement in the image image plane is given by this multiplication. So here, left-hand side is simply a matrix multiplication. What's that? We have first row, first column multiplied to get B. And second row, first column multiplied to get A plus B. So alpha beta, which is the movement of the image point, is governed by the input movement, which is A and B, but it's different, not exactly A and B, but it's governed by A and B. And the formula is that in X direction, it moves by B amount, and Y direction, it moves by A plus B amount. So for example, if 1, 1 moves in the direction of 1, 0, how does the image move? The image point is moving 0, 1 direction. Why? Because 0, 1, 1, 1 multiplied to 1, 0 is equals to 0, 1. So this is the input, change of input. And this is the change of output. Okay? So differential actually relate the change of input to change of output by the matrix multiplication. That's the meaning of our differential here. So we are going to talk about today, we're going to interpret this meaning of differential in many different ways, but also more importantly, we're going to talk about the chain rule, how the chain rule makes sense. I'm not going to prove the chain rule, just want you to understand why chain rule makes sense, and also you need to understand what is the chain rule. But before, if you have any trouble understanding the meaning of differential, let me know right now so that I can explain it again. So if you're not fully understood, not completely sure about the thing that I just explained, let me know right now, or it's gonna confuse more. Say it. Meaning of this matrix multiplication. Okay, so you have an input as a change of, you have a change of input, which is the vector, which gives you the change of your input points. Okay, then in order to find out how fast and in what direction your output point is going to move, you need to take the matrix multiplication with the differential. So here, let me write it again. So again, I think it's better to make a picture again and then write. So U, V are mapped to X, Y, and here's my U0, V0. Here is my X0, Y0. Assuming that my U0, V0 is mapped to X0 and Y0, I'm just started to move my point U0, V0 in AB direction. Okay, so this is my this direction could be my entire direction if I'm moving along the line, but it could be a tangent direction, assuming that my in actual path is somehow like a curvish curve here. But I don't care about the path. I just care about the direction and speed when I just started to move. So that's my vector AB. Now, I can trace the point in my yellow curve, and then how these points are mapped into the image space. So let's see, this is my trace of image. Okay, so if I say this is CT, then this is f of CT here. So again, I'm not really care about the entire path in the image. I only care about at the beginning, when I just started to move my input point, how does my image point x0, y0 just started to move? Just give me the direction and speed where my image point starts to move. That's going to be the alpha and beta. So how do I know to get alpha and beta based on the information of A and B? So can I get alpha, beta, the speed and change of my output, by knowing the input change? If I know the differential, that's the meaning of differential. Yes, you can have your alpha, beta once you know the differential. So df, which is given as f of x, fy, so df given by, assuming that f is function that maps uv to xy, it's xu, xv, yu, yv. And if I take df at u0, v0, it's going to be the 2 by 2 matrix. And then if I multiply that to, so if I multiply that to a, b, then what I get is xu, xv, yu, yv computed at u0, v0 multiply to ab, and you get still 2 by 1 matrix once you multiply these two matrices. The result is actually same as alpha and beta, the output movement. That's what it means.
While we differentiate with our differentiation, matrix multiplication, we get a change of direction.
Can you say it again? So I understood that you have AB, the change of input. Yes.
If you multiply by the differentiation, yes, like.
Yes, 2 by 2 matrix. Yes.
We take like change of direction at the velocity, right?
Change of direction. What do you mean change of direction? So your path is already fixed. Okay, so you are moving in the yellow direction, yellow curve. So here you're moving along the yellow curve. Suppose that your path is fixed. Then your image path is also fixed. Okay, you're not changing anything. It's fixed. Everything is fixed. But thing is, if you're just interested in your initial movement, the entire path doesn't really matter. So if you're just moving in these directions, I only need to know, without knowing exact path I'm following, how fast and in which direction my image point is going to move. Okay, so it's not changing the thing. So although it's changing the shape of the curve, but it's just about estimating how fast or in which direction my point will going to move in the xy plane. Okay, and also be careful about your differential. This differential is going to be changed. The entries are changed when you change your base point. So it only applies when you're moving point here. So if you're taking point the other way and then taking the same vector, we're gonna have a different outputs. Okay. All right, so here's the chain rule on the single variable case. So let's think about this way. Again, we're going back to the meaning of differential. This is the statement that you're probably familiar with. If you have two functions, single variable functions, and you composite together, if both functions are differentiable, then the composite is also differentiable, and the differential of the composite is same as the multiple of differential of each function. So that's the rule. Now let's think about this rule in a different perspective. Which perspective is it? So I want to think about the function f of x first. And then x is a position. So it's a variable that marks the position of a point, right? I want to change the perspective of that, looking at the function here. Instead of marking every point and finding the value of the function at each mark, I'm going to imagine that my mark is moving through the time. So I'm going to introduce another parameter, t. So my x is governed by time variable t. So we have two variable here, x and t. And there are two ways of looking at the value of function, either through the space variable x or time variable t. But really it doesn't matter whether you look through the time or space, because it's all continuous. Once you have a time, you have a space, you get the point. And once you get the point, then you get the function, right? So whether or not it's a function of t or x doesn't matter. So I'm going to write this composite as simply f of t, okay? Meaning that I'm looking at the same function but in a different perspective. So if you just follow the same formula of the chain rule of single variable function, you can have this formula. So instead of gf, using fc, you get the same formula, exactly the same. Now, let me write this in different formation. So on the left-hand side, it's a derivative of t. And on the right-hand side, it's a derivative of x and multiple of c prime t. So that's what really chain rule of single variable function says. If you look your rate of change of a function over the time, it's same as looking at its rate of change over the space and considering how point is moving over the time. So it's just change your perspective. You can change the perspective from space to time, but the chain rule says the result doesn't change. It's the same thing. So let's look at this one. It's a moving picture, but the PDF doesn't makes it move. But we have a parabola function, f of x equals to x squared. And now you're imagine that x is ranging from, it is a point from -1 to 1 or whatever, but I made this point move. So I have ct, which is the t is a time parameter, and when t goes from 0 to 2 pi, it moves from 0, 1, -1, 0, and bumps around -1 and 1. So it's oscillating here. So you have a movement of your point x over the time t. First, let's think about the value of function changes over time, which is ft, and that's given by fct. So that is ft. When I know what time it is, I know what the value of function is by taking the square of sine t, right? Now, let's think this way. I just want to measure how fast my function change. So I take the position where I'm at, forget about the time. I get the speed of the value of function, speed of the change of value of function, and then I just take the speed of my point moving. So and then multiply it together. So what is it? So f prime x is 2x, and c prime t is cosine t. Now x and t are not independent. As I said, x is the position moving in time. So I can convert x into terms of t. So it's 2 sine t cosine t, right? That's f prime c prime. Now, what is f prime t in the first place? If I look my function just in over time, forget about whether it's a function of space or what, I just have information of what time it is, then I know what the function is. Then I can just take the differential in time. So you get 2 sine t cosine t. They're the same thing. You can see that they have the same formula, right? So you may think this is obvious result, but it's important because I'm going to generalize it to several variable function. So look at this one. So let's say we have now two variable function, real valued two variable function, and I'm going to change my x and y along a curve ct. Again, now changing the perspective. Instead of looking at the function as a map between a point to a value, I'm going to look at the function that maps time to the value, because my point will going to move along this curve over the time. So in that case, I can think of this function as a function of time t, so it becomes just a single variable function, right? So when I take the derivative of a single variable function, it's same as the f prime. It really is f prime t. Okay, and what chain rule says is that it's same as looking at the derivative or rate of change over the space multiple with the speed of the point. So f of x here and f of y is the rate of change of your value of function over the space in direction of x and direction of y. But also, you need to multiply the speed of x and y coordinate change. So then, if you do the second way of measuring the rate of change, it's same as measuring the speed of f, change of f over the time. So that's what the chain rule means. And this is not very special. We don't even need to prove it because it comes from the meaning of the gradient. So if you move along certain directions and what you're trying to get is the rate of change, then you just want to get the directional derivative. And we know that directional derivative is same as the gradient inner product with the velocity. And if you just expand this part, it's exactly same as the right-hand side on the chain rule. And on the left-hand side, this is the same as the rate of change of function over the time, the same meaning. So we don't even need to prove it. But let's look at the example here. So we have, so the picture is for some other reasons, but let's concentrate on the formula first. So we have two variable function, f of x, y, which is the shape of the graph is parabola. And we have another curve in two-dimensional space. Actually, that's not the same picture as this one. Sorry, it's a saddle and this is not a saddle. Anyway, so f prime, so we have f and the c, okay? So if I just have a function f, it has a lot of information. If I know any point in two-dimensional space, I can find out the value of function. But what I want is I want my point move along specific curve, this curve, ct. So it's given as a formula, but you can see that actually it follows this one. So this is the shape of the curve. So I only want my point move along this curve So, and also it's determined by the parameter t, which is the time parameter. So I can think of my function as a function of t. So ft is going to be just single variable function which determines the value of function, and it's obtained by simply composite these two functions. So when I have time t, I know where the point is by looking at the curve c, and when I know what my point is, xy, then I can plug that into the formula x squared plus y squared to get the value of function. So what is it? It's a sine squared t plus cosine t sine t squared, right? So that's a single variable function. It makes sense because I don't care about what actually the function is. I only care about at what time what my value of function is. But then you can have, don't forget about the information of space. I just keep the information just to know how fast the function changes in x and y direction, and can take consideration of the speed of each x and y coordinate and take this computation and then try to see whether these two computations are equal when I take the differential. So first of all, f of x is 2x and f of y is 2y, and you can see that f prime x is now x. This is x. It's a x coordinate of the curve. It's cosine t, and y prime is the derivative of this one. And if you put all this back into here, you can see why this is true. So I'm gonna do it together because we kind of spent time before we begin. So I'm gonna let you do other exercise later, but this one we can do it together. So here, f of t is, forgot the formula here. So we have sine first, right? Yeah. It's sine square t plus cosine square t sine square t. And that is actually coming from f of ct here. And ct, let me write ct anyway, is sine t cosine t sine t. So c prime t. So in fact, when you take the differential of a parametric curve, it's a vector. So I'm going to write as a vector notation. Cosine t minus sine square t and plus cosine square t. Okay, so let's first find out what f prime t is. Okay, so I simply take the partial, just ordinary differential of this one variable function, which is 2 sine t cosine t, and the second part is 2 cosine t sine cube t, and I think I need a minus here, and then we get 2 cosine cube t sine t. Okay, that's our f prime. So what about fx x prime plus fy y prime? So fx is 2x, x prime is cosine t, and fy is 2y, y prime is minus sine squared t cosine squared t. And 2x, what is x? It's x coordinate in ct. It's sine t, so it's 2 sine t cosine t. And y is the y coordinate in ct, so it's 2 cosine t sine t. And then you have minus sine square plus cosine square. So you can see that this thing appears here, right here, and this thing appears right here, and this thing appears right here with multiplication of this. So you can see that left-hand side and right-hand side of the chain rule are the same. So you can say chain rule works for this example. It doesn't prove the chain rule, but you can confirm that it's true. So let's do it a little bit, make it bigger. Let's make the case a little bit bigger. So what we are going to talk about is, first, take the map T, which maps the point in UV to XY, and I'm going to take a parametric curve on UV plane, which is CT. So, and then I'm going to take a composition of T and CT. So here, T is T composite CT. So same thing that I explained in the beginning. So we have T maps a point in UV plane to XY plane, but instead of point, I have a curve. So the curve is mapped to another curve. If I trace the point in the curve and put it in the image, then I get another curve in XY plane. That is going to be called TT. Okay? Now, what does it say? What does the chain rule on this situation say? It says, so if I denote the x and y coordinate of my curve on the image domain as x and y, then the velocity of that curve is given by the matrix multiplication, which is the differential of the function t and the matrix given by the velocity of the curve in the domain space. So here u prime v prime is the velocity coordinate of the velocity of your original curve, and x and y are the coordinate of the velocity in the image. However, this is actually the same meaning of differential. This is the meaning of differential. This is exactly the same, has the same meaning as the differential. Because if you start to move in u prime v prime direction in your UV plane, you're gonna move in certain direction in speed in the image space. How do you get that velocity? By taking multiple of differential with that velocity. That's the meaning of differential. And chain rule here says exactly the same thing. So I'm not proving the chain rule. I'm just state the chain rule and convince you why the chain rule should be true. Let's look at this example. I'm gonna let you do this one. So here we have, so by the way, this image is not a correct one, so ignore this image. Let's say we have this function t, which maps uv to xy, and xy has a formula of v and uv, with same formula we just saw in the beginning of the slide. And we have ct, which is the curve in the uv plane. So this is curve in uv plane. Okay. Now, dt, so it's actually tt in the previous slide. This is same as t of ct. Okay, so you can find the image curve corresponds to the curve ct, and you can find its derivative, the velocity at each time. That's your d prime t. And now let's try to get the same velocity without taking the derivative of dt directly, but taking the derivative of the t 2x2 matrix and multiply with the derivative of the parametric function c. And then you can compute this. So c prime t, by the way, should be considered as 2x1 matrix here, and dt is considered as 2x2 matrix here because of the definition of differential. And what you need to do is see whether what you get for d prime on the second stage is same as what you get for the third stage by multiplying two matrices. So I'll let you do some calculation in your group. So one person for each group, one person come to the front and take some piece of the paper and pencil or pen, and if you have any questions, let me know if because I'm going to walk around. Okay, I know it's notation a little bit confusing because I mixed up some of them. So let me do it together here. So and the more important thing is not actual computation. You need to understand the meaning of this. But I'll show you the computation wise it also works. So let me say, okay, so we have ct is sine t, cosine t, sine t. I'm not gonna finish maybe all the computation, but just giving the idea what it looked like. So you have this situation, which is, so ct is already this shape graph. It's sitting inside this UV plane, and I don't know what this look like in XY plane, so maybe some crazy shape like this. Anyway, so this is my CT, and I want to find the DT, the coordinate function of DT. In order to find, need to take the composition. So that's my DT. So it simply takes coordinates u and v in the place of uv in the t. So it's a t of sine t and cosine t sine t. So it means that whatever you have u in the output, you plug in sine. Whatever you have v, you plug in this. So it's cosine t sine t, comma, cosine t sine t squared. So that's your dt. So now we have ct and dt, and let's find out the, so I think that I choose the wrong letter because it's all confusing. Now let's take about dt, so another dt. So it's a 2 by 2 matrix, differential of t. We already done this, so it's vu. Now, what we want to show is c prime dt is equals to d prime. Okay, so I'm going to compute this part and this part separately and then see they are the same. So dt times c prime is same as 0, 1 vu times c prime. So what's c prime? Since c is a function from one-dimensional space to two-dimensional space, c prime means it's a differential, which is 2 by 1 matrix. So it's u prime v prime, which is c t, this is u t, and this is vt. 0 here, something went wrong. Okay, so here, this is 0, 1 vu. I'm gonna leave v and u here just for now. So now instead of u, I need to put u prime, which is derivative of sine, which is cosine, and v prime, I get minus sine square plus cosine square. So that gives me minus sine square plus cosine square. And on the second row, we have v cosine t plus u minus sine square t plus cosine square t. However, as I said, u, v are not independent to t because they are moving along the time frame. So we need to switch back this uv in terms of t. So then what we get is, it's going to be long form. So let me write it here. So minus sine squared t plus cosine squared t. And v is cosine t sine t. So if I multiply it together, I get this. And u is sine t. So I get sine t minus sine t squared plus cosine t squared. So that's my dt times c prime, which is the right-hand side of the chain rule. Now I need to compute the d prime, which is on the left-hand side of the chain rule. So when I do this, what I get is I need to take the differential of this. Okay, so first I get d dt of sine t cosine t, and the second I get d dt of cosine t sine squared t. So the first part is simple. It's cosine squared t minus sine squared t, which is already, you can see they're the same. These are the same. And the second part, it's minus sine cube plus 2 cosine t sine t square. So I think there is, well, let's see. So here we have sine cube, same thing here. And we have twice of cosine square sine here, right? The same as this one. So you can see that they are the same. Okay. So it's a simple calculation. Once you know the formula, it's about the simple calculation. But we're going to actually find out why is it important. I want to tell you why it is important. So instead of this example, I'm gonna explain this one, the picture here. The picture here is actually what we want to do the coding here. So I'm going to give an example. Ct is cosine t sine t, where t is in the range of 0 to 2 pi. And I have t uv as v uv. Okay, so and then dt is simply t of ct. So same format, almost same, except that we start from different curve on uv plane. So this is the curve in uv plane, and this is a map from uv plane to xy plane, and this is the image of ct in xy plane. So what we want to do here together is we want to make a moving point, and I want to relate the velocity of the movement of a point in the uv plane to the velocity of the movement of the point in the image plane. So there are two ways of doing this. First of all, the movement of the uv plane can be done easily because there is only one function. But on the image plane, there are two ways of to pictorize the vector of movement. One is you can find the formula of dt and then take the differential, just as we did in the left-hand side for the chain rule, or you can use the right-hand side of the chain rule. Just find the differential of the t and then multiply it to tc prime. So the task is draw and animate the vector of movement of the point of ct and dt. So, well, let's do it here. So is it clear that what we're going to do? So we are going to produce the picture, the moving picture that you can see on this right-hand side. So not this one, right here. We're gonna make a picture like this one. Okay? Are we clear? Okay. So let me open up the collab here. Okay, so I hope you guys follow me because we're going to use a different package to produce an animation. So it's going to be fun, and also it's what I really wanted to do on the morning class, but we didn't have time. Okay, so let me prepare some few ingredients here. So matplotlib, splt, and also we need matplotlib animation as animation. Okay. So we need to define a function c, right? So I'm going to define, is it too small? If I can't make it too big. So, okay, so I want to define my function. It's going to be the numpy array of numpy cosine and numpy sine. So every time I take t, I'm gonna get the numpy array of these, and I need the velocity. I can get the velocity by approximating its derivative, but I can just, since I know the formula, just write it as a function. So my c prime, named as cp, is going to be numpy array of minus numpy sine and numpy cosine. Okay, once I have this, what do I need? I need a map. I need a map that sends uv to something xy, right? So instead of taking two arguments, I'm gonna take one argument as if the one argument is two-dimensional numpy array, which is x. So if it's confusing to you, I'm gonna name it uv. So the output is numpy array of uv1, which is v, by the way, and uv0 times uv1. Okay, so uv is just the name of the input. Okay, and uv0 represents 0, uv1 represents v. So I'm making uv goes to v uv, right? That's my t. And I also need the dt. So dt is going to be the lambda of uv. Again, so derivative, the differential always has to be computed at some point. Okay, as you can see from the formula, it has a u and v. So I need this. So remember that what the thing was? It was what 0, 1, v, and 0. Okay, that was this. Okay, we have dt. Now, let's first make a picture first. So I'm going to let my t to run through 0 to 2 pi. 2 pi is numpy pi. And I'm going to split the view of two windows, one for uv and one for xy. And here, fig x equals to plt subplots 1, 2, and so what I'm doing here is I'm trying to make it as make the window axis window as a list of windows. So that's what I'm doing here. X.revel give me the list of window. And for the first window, I'm going to plot CT. So I'm going to plug this t, the list of values from 0 to 2 pi, into here, right here. Then what it gives me is, so when t goes here as an array, then it's not a 2 by 1 matrix anymore. It's going to be 2 by the number of array of t matrix. So it's going, so then I need to take the zeros row as my x coordinate and first row as my y coordinate list. And for the second part, what I want is, I want the composite. I want the image of the curve C. So I'm going to send my C to D to get the new coordinate, right? So send TCT inside T to get the new coordinate. And then I'm going to draw this. Okay, so I don't need show here. Anyway. So you can see it's not, in the same scale, but it shows well. The first window is the circle, and the second window is the bow tie shaped curve. So without getting the formula of D, I just use the function which is given in the beginning and produce the same figure here. Now I want it move, but I just want to keep the trajectory here, and I just want the point move. So let's make the point move from here. So I'm gonna write more. So if you want to see what some part of the code? No, it's okay. All right. So I want to make the point move. So I'm going to define update function. So this update is for later use. So here I'm going to, I forgot the name of that. What was font animation? Yes. So fig update frames. So okay, so frame is lengthy, interval is lengthy. Okay, so you have to write this out. Save. Okay. So I think I showed you before a little bit while ago how to make an animation by producing a zip file. So this is how it's done. It's using an animation package in the Matplotlib. So I imported the animation package as the name any here. And in any, there is a function called font animation. It takes some argument, and you have to follow the rule. The fig is already taken from this method here. And then update is what actually updates the frame. So I need to put some content in the function called update here. And I is representing the ith frame. So you need to specify number of frames that the GIF contains and the number of intervals that going to iterate. But usually I set these two as an equal number. So what does update do? So instead of, so I already plot this two. I'm going to define UV point and XY point. So UV point is the first axis window plotting the point CT. Actually, in here you don't need anything here. So we're just going to empty this RO here. And XY point is a point on the first window. So I'm going to empty out at the beginning because I'm not going to draw anything at the first. But when I update ith frame, I'm going to update the data of that drawing. So let me check. So that's right. Yeah, that's right. And then return this too. So you have to write exactly the same. So you can change the name of UV point and XY point, but what goes inside has to be the same. So what it says is that I just initialize the name, variable name UV point and XY point so that I can update the data in it. So whenever the update function is called at the ith position, then I get the coordinate of the point C and the TC, and then put that in the data set of this UV point and XY point so that each frame contains that point drawn into the axis window. So, okay, so I think it should so sometimes ImageMagick is not installed in your local machine, but you can install it. Maybe let me check whether I got it already, but okay, so here. So try to finish the code anyway, and then if you run the code, if it doesn't work, let me know. Okay, so if it doesn't work, let me know how to install this ImageMagick. And so even if there is a warning, the output is here. You can see that it's the GIF file that contains the animation. So finish writing the code and then see if you can get the output GIF as a GIF file. Anyone have trouble making into GIF file? Raise your hand if you got the GIF file. Not yet? You got it? Okay. So I think you can ignore the warning. So shows you the GIF file anyway. So well, I'm gonna give you some time to finish writing the code, but meanwhile, I'm gonna tell you the plan. So now we have a moving point. You can see that this movement is according to the mapping. So when the point on the left is moving, the point on the right is moving accordingly. We want to put a quiver, the arrow, which represent the velocity of each point. Okay, so on the left hand side, we already have that velocity, which is given by Cp. We already defined the CP. But on the right-hand side, we didn't even put the formula of that movement. We didn't compute the dt. We simply plugged that ct into the function t to find its coordinate. How do you get the velocity quiver, velocity vector? So in order to draw the arrow, you need to find out x and y coordinate of your vector. So question is, how do you find those x and y coordinate of your velocity vector? So once again, if you compute all the formula for dt, the right-hand side movement, then you can take another derivative to find its velocity. However, you don't need to, because we have a chain rule. What does the chain rule says? It says you can simply take the multiplication of the differential dt, which we already defined, to the velocity of the original domain space, right? So raise your hand if you got the GIF by now, so that I can move on. So you got it? Got it? Anyone else? Got it? Did you got it? Are you working on it? No? You're not working on it? No? Doesn't move? Okay, so but you got the GIF? Do you get the GIF file? So you just type the same thing and then run this. Anyone else? Yes. Just just type the same thing and then you can see the file. So don't forget, you have to type in exactly the same. Here is a comma. Okay. You need to type the comma here. Comma here. Not a typo. This is not a typo. Okay, let's put the quiver. Let's put the arrow. So we need arrow box. So I'm going to put UV quiver as axis 0 quiver. Here it's a long, so I'm gonna use the quiver param here. T quiver param. Okay, so yeah, sometimes scale unit is not unit scale unit angles. I don't think we need this necessary. So okay, so you want to put the quiver param as a dictionary type of these values, and I'm going to put that as an option. And same thing for quiver on XY. Okay, so I just put these parts in between the definition of update and the point drawing. So I think we will adjust a little bit on the scaling factor, because normally the size of arrow will go extend this box here. So we're gonna do it next later, but for now let's put it as 1. Okay. So every time I update my frame, I'm going to update the quiver, right? So UV quiver. I'm going to update the UV quiver first. Um, um, what name of this? Let me go check really quick about. So not only my quiver changes this direction, I also want to start my quiver at the new position because the point is moving. So I not only I update the size of quiver, but also I need to move my quiver starting point. So I just forgot the command for that. So by the way, so let me explain this. So UVC is a set UVC sets up the data for the quiver size. So the quiver size is given by the derivative of the parametric function, parametric curve, so which is CP. So I just look up the ith position zeros factor and ith position 1 factor to get the x and y coordinate of my vector velocity. Let me go really quick about here. So let's see. Uh, uh, there's somewhere I used my arrow offset. Okay, so it's offsets. Okay, so here set off. Okay, yes. So I can change my starting point, which is called offsets, to the starting point of that to the point where my point is at. Okay, so here we have UV, XY quiver, and so on. So I didn't update XY quiver, but let's see what happens here. Oh, there's an error here. So Okay, so I should not put the, so just delete the comma here. For the quiver part, should delete the comma here. For the plot part, to get the plot, you get the comma. You should put the comma right here. But in the quiver part, don't put the comma after. Okay, so something is done. Let's see if I can get the right one. Okay, so I think there is a I think there is arrow. It's too small. Is it? Why I don't see any. Okay, maybe I change it to 0000. So let me try with this. Sometimes works this way. So instead of empty list on the quiver argument, I put zeros instead. So let's see the result again. Okay, so now I get it. So you can see now there is a arrow from the point. Every time it changes the frame and position, the quiver starts at that point, and you can. But it's only because it's squeezed, it's not scaled properly. So you can change it. You can change the scale here. So if you want. So let's see. I want fig to have set side inch by 2 by 1. So let's do it again. So you have, if you have this option, then you get, I think, better picture. Okay, so now you get better picture. See that the pivots are here. Now, let's not bothered by arrows going out of the box. For now, what we want is I want to put the quiver on the right. Okay, so that's my goal. So instead of calculating dp or calculating d anyway, I'm gonna find the coordinate of my quiver on the right. How? So here, I want to set my quiver xv plane to be offset by I position of my D point. But how do I know the size of a quiver? So size of a quiver is given by AB, which is quiver. T, so what is dt? So compute the differential at the t at the point ct I. Okay, so this is your current point at frame I. So at the frame I, you're at the ct position, right? So and then you get the dt, which is 2 by 2 matrix. You multiply with your c prime t, right? So c prime t get it by this. So I'm not sure whether it could have an error if I just run this way, but the idea is I get the Cp, the C prime, multiply to the differential to get the velocity of dt. So then I'm going to put that into my update of quiver on xy plane. Xy quiver set UVC to quiver 0 and quiver 1. So this quiver QV contains information about my size vector, and I'm going to check whether this works fine. Problem here. So I think there's a problem. So this is 2 by 1, I think. This is 2 by 2. This is 2 by 2. Fine. Let me check whether what's the problem here. dt. Okay. So here, index out of range. Let me check whether it's fine. Or let me consult my code here. Sorry for bothering. So, okay. So, I want to make it work. UV1, UV0. Oh, okay, okay. Now I got it. So need one more parenthesis. I forgot one more parenthesis to make it into 2 by 2 matrix. Okay, so here I changed it, and let's run this again. Okay, now it's working. At least no error here. Okay, now it's working. So you can see that on the right hand side, you have a quiver again. And the quiver is actually a tangent quiver, a tangent to the curve. I didn't get the quiver by calculating or taking differential of the formula of this of the second curve, but I only take the matrix multiplication based on the velocity of the domain. Taking multiplication with the differential, I get the quiver on the right, on the image space. Okay, so that's the meaning of chain rule. Basically, you can apply the chain rule when you draw something. Okay, that's what I wanted to tell you. So formula is important, and also the meaning of everything is important, but more important thing is how you can apply this chain rule when actual computing. So this is how you can do it. So I'm gonna upload this code again, as I did always, and the next time we'll talk about the rest of the part about the chain rule. I mean, there's not much more left in the slide, but also we're gonna talk about next time after the midterm week, the fifth project on drawing the what is it, the heat line, heat flow, and then this chain rule will appear in our sixth project about the neural network. Because in the neural network, what we really do is using heavy use of the chain rule to update your parameters. So you have to understand the chain rule. So don't try to understand the chain rule as a formula. Okay, so understand it as a concept that you can get change your output simply by taking a multiple of differential on the change of inputs. Okay. All right. So if you have any questions, let me know, or we'll see you on next Wednesday. Yes. Okay. Who told you? Is I. Would this one be? Oh, DT here. There's another. Alt 6 XY reverse alt positional is on given. Ah, anyway, so DP on 1 0 0. Oh, why do you get the minus here? Why do you need minus? I think it works now. Okay, okay, and how do all that to represent midterm projects be created randomly or in the presentation order? Yeah, so it's random pick. Thank you very much.
혹시 이 발표 순서는 어떻게 되나요? 그러면 다음 주 수요일에 와가지고 추첨을
예.
다음 주 금요일에도 와야 되는 만약에 수요일에 한다면 금요일에 올 필요는 없는 거죠? 네? 그러면 수요일 날에는 꼭 참여 수요일에 몇 시쯤에
그냥 수업 시간.
왜냐 팀원분이 수요일 날에 병원 예약했다고 그러시는데
뭐 그런 경우는 뭐 어떨까?
금요일도 네, 금요일도 안 된다고 그래가지고
뭐 그런 사람이 이제 다음에 가는 거.
그러면 두 명이서 발표하시면 선물 받고 있어요.
그러면 다 하세요. 그런 사람은 없을까?
그러면 줌으로는 진짜 안 된다는
이거는
아니 그냥 온라인으로 하는 거는 안 되는
아예 뭐가 불만이 많아.
그러니까 아니면 그러면 이제 저희 두 명이 발표하고 나머지 한 분한테 교수님이 서로 물어보는 방식인가요?
그 친구는 넘어가겠죠. 그다음
저희가
발표하면 다 지원 전체가 다 발표.
뭐한 사람씩 할 필요는 없어요.
저희 지원 임의로 그냥
다 있어요.
다 현장에 다 있는데 발표하는 거 그냥 그러면 수요일날 랜덤 풀어서 맞았는데 영어를 못해서
그냥 우리 템플릿 하는 거 있잖아요. 그거 이제 내용을 그걸 카피해가지고 한글에다 붙여놓고 한글로 쓰라는 게 아니야. 이거 파일 자체에다가 쓰라. 텍스트 파일, 그냥 텍스트 파일, 텍스트 파일 안에다가 넣고 그냥 그대로 올리면
LMS에 나중에
LMS에
수요일이랑
그런 거 있으면 이제 뭐 수요일에 먼저 하겠다고 그때 가서 다시 그렇게 나오는 거. 파일을 제가 다운받은 이거 내 폴더에
지금 발표할 때 저희가
그냥 생긴 게 어려운 건데 기억상에 4이 88이 그냥 17중 8이 몇 번째 판에 글자가 들어간다고 외국어를 쓸 수 있어요. 그러면 첫 번째로
그냥 이 588, 28이 뭐냐는 정도만 네.